Chapter 8, Chemical Reactions. Sections 8.1 and 8.2 we're going to combine together and talk about equations for chemical reactions and balancing equations. When you have a chemical equation, it represents a chemical change or a chemical reaction. And you have the format where you have the reactants on the left side, the arrow meaning yields, products. Okay? In a chemical reaction or chemical change, mass is neither created nor destroyed. This is the law of conservation of mass. Because mass is neither created nor destroyed, just changed from one form to another, the number of atoms of elements must be the same on the reactant and product sides. In order to account for this law of conservation of mass, we balance equations. Okay, because in reality, this is what happens because of the law of conservation of mass. So we're going to talk about some things that we see in chemical equations, and we're going to talk about how to balance chemical equations, followed by different types of reactions and balancing more equations of different types of reactions. To balance equations in accordance with the law of conservation of mass, we will use the lowest set of whole number coefficients. These numbers are going to be placed before the chemical formulas, and they apply to all the elements in the formula. When we start to balance equations, we will not touch the existing subscripts of the formulas that are of the reactants and the products. We will only use these whole number coefficients when we get to when we start to balance equations. Some other things that we need to point out about chemical equations before we start to balance them. You will sometimes see symbols in the chemical equation which represent the state of matter or some other reaction condition. If you see the letter S in a parenthesis, that means that it is a solid. An italicized or script handwritten L is for a substance that's a liquid, and G for gas. If something is dissolved in water, it is an aqueous solution. Aqueous, aqua, water, Latin for water, aqua. You see AQ. So that means that whatever that formula is for that substance, it's dissolved in water. It's an aqueous solution. Some other reaction conditions, when you see a triangle over the yields arrow, that means that heat is applied to the reaction. And sometimes you have a catalyst that is used to speed up the reaction. It's not a participant in the reaction. It simply helps to get the reaction to go faster. And whatever the symbol for the catalyst is, it would be written above the yields arrow. So I here put a platinum above a yields arrow. A car's catalytic converter, thus the name catalyst, is an important part of the vehicle because it helps to speed up the process for the breakdown of harmful products that result from the gasoline combustion, so that you don't have all of these hazardous particles being released into the atmosphere. The catalytic converter helps with other mechanical parts of the car to break down some of those molecules into smaller molecules like carbon dioxide, water, so that they can be released much faster and to not have a harmful effect as the other ones would. So the catalytic converter helps to speed that process up. But you have catalysts used in very simple chemical reactions as well, and is very advanced like catalytic converter. Our bodies have catalysts, but they're called enzymes. So the enzymes are catalysts, biological catalysts that are in our bodies to help speed up the breakdown of large biological molecules. You have enzymes that break down large sugars and large proteins. So these large biological molecules that need some assistance with being broken down by the body, the enzymes are there for that. Some acids we will see in chemical formulas. Now we will learn more about acids in chapter 14 towards the end, but just to introduce you to some of the common ones: hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, phosphoric acid, H3PO4, and acetic acid, HC2H3O2. So it's usually written in this format here. as opposed to its molecular formula. It usually has the hydrogen separated. So acids contain hydrogen. Generally speaking, we'll learn a more advanced definition later on. But just to recognize some common acid formulas, and their naming system is different than it is for ionic compounds and for the binary molecular compounds. So just some general acids. Lastly, some things that you could see in a chemical equation. You could see the formulas for diatomic molecules. Diatomic molecules, there's 7 of those. They are atoms of elements that when they exist alone and not in a compound, they pair up with similar element, like twins. So we have 7 of them: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And there's a little silly way to remember what the 7 diatomic molecules are. Horses need oats for clear brown eyes. So it's a silly way to remember what those 7 diatomic molecules are. So when they are written in chemical formulas, they're always written as a pair. Okay, I just want to point out some general rules for balancing equations before we actually do them. You're going to see that the textbook will explain it with its twist. I'll explain it with my twist. I put some videos on the course module from Khan Academy. They explain it with their own twist. You maybe learned it before in high school and your teacher taught it a different way, all right? But some people look at it and they say, oh yeah, I just see it. So everybody's different. So one thing I want to point out is that some equations are pretty easy to balance and some are a little bit more involved. Some of them you have to go back, and you'll see this throughout this section and in the next section, section 8.3. You'll see some of them are very easy to balance and some of them need a little bit more thinking involved. So don't be discouraged, just work through it. It's the law of conservation of mass. It's not make the equation work for you, it's how it exists in nature and how it reacts in nature. Okay, just some other things too. A lot of times times tables come into play, remembering your times tables and balancing equations. The Khan Academy video explains it with a fraction concept. I've been teaching this a long time. I think sometimes that way is more confusing to the majority of students that I've encountered, but everybody's different. So as long as you get it, that's the main thing. Okay, so let's go over some of these general rules and then let's do many examples. Okay, we get proficient at it by doing. We need to use the lowest coefficients. So always start off low. Start off with 2. Start off with 3. Okay? We do not change existing subscripts. So if a chemical formula has a 2 or a 3 or a 4, that stays in the chemical formula. You can't slash it out and change it and X it out. The coefficients times the subscripts equal the number of atoms of elements. So whatever's in front of the formula, we're going to multiply that by the subscripts. We're going to see also in this section and in the next section, it helps to balance the polyatomic ions as units. If you see you have a nitrate unit on the reactant side and a nitrate unit on the product side, it helps to keep those together and balance them as units. Keep a tally and work from left to right. Okay, you have to have some kind of organization. Sometimes students get overwhelmed. They try to balance multiple elements at once and get flustered and get upset. So keep a tally, all right, work left to right. Balance one element or polyatomic ion at a time. Okay, and again, we need to remember, as I had it written up there earlier, law of conservation of matter. Okay, the number on the reactant side of atoms of elements must be the same as the number of atoms of elements on the product side. Let's do some practice and learn by example. Okay, let's do an example. I'm starting off with a pretty simple reaction. Solid magnesium, when it's burned in the presence of oxygen gas, gives off a bright white light. It's a really cool reaction. We do it in the lab. Gives off this bright white light. You'll see it in one of the online labs, I believe. Yeah. And the product is, yes, a bright white light in addition to the formation of the magnesium oxide solid, which is a white powdery solid. All right, let's balance the equation. We have 1 magnesium on the reactant side and 1 magnesium on the product side. So far, so good. We have 2 oxygens on the reactant side, but on the product side, we have only 1 oxygen. Now, you may be tempted to say, oh, well, can't I just put 2 there? No. That doesn't work that way. You cannot do that. You cannot change the formula of magnesium oxide. Okay, that's not what magnesium oxide is. This is what it is. So you need to use the coefficient. So coefficient is whole number placed before the chemical formula. Well, now that 2, now we have 2 oxygens. But we now have 2 magnesiums because that 2 in front of that formula applies to everything in that formula. So now we have 2 magnesiums and 2 oxygens. Well, we look back over here, okay, yeah, we have 2 oxygens, but we only have 1 magnesium. We need to put a coefficient of 2 in front of magnesium. Okay. It's always good when you're balancing equations and you're first starting off, use a pencil because sometimes one coefficient doesnn't work as you'll see, and you may need to change it. So it's good to use a pencil so that you're not making a big mess and confusing yourself unnecessarily. Okay? So 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens. Let's do another equation to balance. Let's take methane gas, okay, which is the what mainly is natural gas. Burn that in the presence of oxygen. This is what your most homes have methane natural gas heat. That's a PGW has as output. Produces carbon dioxide, water, and it also produces energy. We are not going to worry about the energy component of it for Chem 110. Chem 121, you have a value in kilojoules for each reaction that is similar to this, a combustion reaction, but we're not going to worry about that for now. But I don't want to ignore the fact that energy is produced. That's how you get heat energy for your home, okay? Now, this reaction, we have 1 carbon, 4 hydrogens, and over here 2 hydrogens. All right, let's fix the hydrogens. 2 hydrogens. Here, 2 times 2, 4 hydrogens. Okay, so we're good so far. 1 carbon, 4 hydrogens, 2 times 2, 4 hydrogens. Now let's count the oxygens. We have 2 oxygens on the reactant side. Now be careful with the product side now, because oxygen is in 2 of your products. You have oxygen in carbon dioxide and you have oxygen in water. You need to add those together from each of those compounds. So we have 2 oxygens coming from carbon dioxide and 2 oxygens coming from water. So we have a total of 4 oxygens on the product side, okay? So you have that sometimes where you have an element that is in more than one reactant or product and you need to account for it on the reactant or product side total, okay? So on the reactant side we have 2 oxygens. We need to make that balance out to 4, okay? So we have 1 carbon, 4 hydrogens, 2 times 2, 4 hydrogens, 2 times 2, 4 oxygens, 2 plus 2, 4 oxygens. Okay. All right, let's do another one before we start to talk about reaction types. And when we talk about reaction types, we're going to also balance equations more, but we're going to classify the types of reactions. Let's do a reaction where we have potassium chlorate, okay, breaking down into potassium chloride and oxygen gas. I didn't write the states of matter for this one. I'm just going to move this over here so I don't have to, all right, try to keep everything neat. Given my limited board space in lecture classrooms, I'm so used to a big space to write. So I have to watch the space here. Okay. 1 potassium, 1 potassium. Oops. This is chlorine. 1 chlorine, 1 chlorine. Remember, atoms, symbols for elements, they're either one capital letter or a capital and a lowercase. Okay, chlorine is Cl, all right. Iodine is a capital I, usually written as a, I know that sometimes the font can be a little bit misleading, but usually it's written as a capital I with this top and the bottom stem. All right, oxygens. We have 3 oxygens on the reactant side. And on the product side, we have 2 oxygens. Okay, times tables. 3 times 2 equals 6. All right, let's balance out the 6. If we put a 3 here, that'll give us 6. If we put a 2 here, that'll give us 6 oxygens here. Okay? All right, we got the balance of oxygen now, but we had to put a 2 over here. Now that 2 applies to everything in that formula. So now we also have 2 potassium, 2 chlorine, and 6 oxygen. Well, we need to fix the potassium and the chlorine over here. We need to put a 2 over here. So now we have 2 potassium, 2 chlorine, and 6 oxygens. Okay. Now I know some of you watching this right now may say, I got this. Can you give us a harder one? Yeah, we'll be getting there. And I know that there's some of you sitting there watching it saying, I got to go back and rewatch this. Okay? That's fine. Okay? Everybody has different first reaction to this. Okay? Let's do some more examples where we talk about the different reaction types. And after I do the reaction types, okay, it's very important that you practice on your own and you do the ones that are in the book that I recommend. So you get practice with balancing equations after I have gone through and explained the different types of reactions and shown you more reactions to balance, okay? So let's now go into section 8.3, balancing a chemical reaction types. I'm sorry, types of chemical reactions, okay? Let's do some more balancing equations.